Hi everyone and welcome back to Chemistry Universe. We have done alkanes and today it's the turn of alkenes. Now we'll do alkenes in three parts, and in this part, the first part, we'll be talking about introduction to alkenes and methods of preparation. And this is going to be a relatively very short video. And the next part, of course, would be the properties of alkenes, which will be very, very long. So this is going to be short. The next one is going to be long. So I think you'll be able to handle them. But again, make sure that you take notes while watching the video. Pause as many times as you want. Write them. Just take it as if you're taking it in the class. Just attending a class. The only difference being that you're not physically present in a class. But everything else you must duplicate as you would do in the class. And that way you will learn more and you will learn better. So, with that being said, let's start with the part one of alkenes, that is introduction and methods of preparation. All right, so here we go. Introduction to alkenes. Now, these alkenes are also known as olefins. That means oil forming. Now, what this basically means is that most of the oils that you see, we call them as unsaturated fats because they're liquid, and that is because of their unsaturation. You must have heard of the term saturated fats. Now, saturated fats are the ones in which there are no double bonds, all bonds are single, which means they can better fit into a crystal lattice. And therefore, all these saturated fats are what you find as semi solid in shape, whereas like butter and stuff like that. Whereas the unsaturated ones are the ones which are the major component of oils. Now, the general formula we all know is CnH2n, and they contain C double bond C. But remember, just because something has CnH2n doesn't mean it's an alkene, because CnH2n only implies there is one unsaturation. Now, alkenes are nucleophilic and therefore tend to react with electrophiles more often. Now, this is something which we will do when we do the chemical properties of alkenes, and that is to say that the alkenes have a pi electron cloud, and this pi electron cloud has a tendency to attract electrophiles because they are electron rich. Alkenes are electron rich, and electrophiles are electron deficient. So, the alkenes tend to attract the electrophiles. So, most of the reactions of alkenes are electrophilic in nature. All right, so let's look at the methods of preparation. The first one is by catalytic hydrogenation of alkynes. Now, we have discussed this in alkanes. And in alkanes, we said that if you hydrogenate an alkene, you'll get an alkane. If you hydrogenate an alkyne, you'll get an alkane. And I told you at that time that it's difficult to stop it at alkene stage, but you need to use some special catalysts. And this is exactly what we're going to do now. We're going to use those special catalysts to stop the alkyne at the alkene stage itself. All right, so the first is by using Lindlar's catalyst or nickel boride, alkynes can be partially hydrogenated to alkenes without their further hydrogenation to alkenes. So let's understand what is this Lindlar's catalyst. A Lindlar's catalyst is a heterogeneous catalyst that consists of palladium deposited on calcium carbonate or barium sulfate, which is then further poisoned with various forms of lead or sulfur or quinoline or xylene. Now, this is something we are hearing it for the first time, so let me make you understand what I'm trying to say. In hydrogenation, I had discussed that alkynes have a higher tendency to get hydrogenated than alkenes because of the two pi electron cloud, number one. Number two, the fact that alkynes are linear in shape. So, if there is a catalyst like this and you have an alkene, now the alkene has to make sure it is parallel to the catalyst to get hydrogenated. If the alkene rotates in this axis, if it rotates, it cannot. If it rotates in this axis, it cannot. So it has to make sure that it is parallel. So its effective collisions are relatively less. Whereas if you look at an alkyne, catalyst is there and the alkyne is here. Now if the alkyne rotates through this axis like this, then of course there is a problem. But if it rotates through this axis, it still remains as it is. So what happens is that for a linear molecule, it is much more easy to orient itself to a catalyst to get hydrogenated. So for this reason, alkynes are more prone to get hydrogenated or more easily hydrogenated or more reactive towards hydrogenation than alkenes. Though remember, when we discuss alkynes, we'll say that most of the other reactions, the electrophilic reactions of alkynes, are much slower than alkenes. But for hydrogenation, alkynes are better. So what happens is you have a catalyst and you have an alkyne, and there is this alkyne here. There's a catalyst here. You get hydrogenate the alkyne to alkene, but once the alkene is formed, now the alkene is also parallel to the catalyst, and it will still get hydrogenated to alkenes. But if I poison the catalyst, meaning I reduce the number of reactive sites, so only the most hydrogenatable, if I can use the term, the most hydrogenatable molecule, which is an alkyne, can get hydrogenated, but the less hydrogenatable one will not be able to get itself attached to the catalyst because of less active sites. And therefore, alkynes will become alkenes, but the alkenes will not further go to alkenes. So how do we poison it? We take palladium and we add barium sulfate or calcium carbonate to it. That itself will act as a poison. Sometimes you might need additional poisoning, and later on I'll tell you when you would need additional poisoning. That can be done by sulfur or lead or using quinoline or xylene. So these are additional poisoning agents. So this entire thing is called a Lindlar's catalyst. Alright, so here you have an alkyne with H2, and as I said, we use the Lindlar's catalyst, PdCaCO3, poisoned with sulfur or lead or quinoline or xylene, which is of course an additional poisoning, and it will become an alkene. Now, alkynes are more easily adsorbed on the palladium as they have more pi bonds. Compared to alkynes, alkenes have only one pi bond and will therefore need more active sites on the catalyst to bind themselves. If we poison the catalyst, the active sites reduce. Therefore, alkynes can bind to it, but alkenes can't, which prevent the further hydrogenation of alkenes to alkenes. And this addition is a syn addition. Now, what you need to understand by syn addition is that I have an alkyne, I have a catalyst, hydrogen is adsorbed on this. The two hydrogens will come obviously from the same side because the catalyst is only on one side. So both the hydrogen will come from the same side. So the addition of hydrogen to an alkene is a syn addition, just like as it was in the case of alkenes. So alkynes will get hydrogenated by this catalyst, Lindlar's catalyst. Again, it is going to be a syn addition. Now, what is the significance of this syn addition? The significance is that if you have an alkyne where you have on one end an alkyl group R, on the other hand, maybe the same or a different alkyl group R or R prime, and there's a C triple bond C. When the two hydrogens come, remember, this is going to turn into an alkene. Since the two hydrogens are coming from the same side, you'll always get a cis alkene. So remember, Lindlar's catalyst is used for the preparation of cis alkenes from non-terminal alkynes. Remember, the alkyne has to be non-terminal, because if it's a terminal alkyne, there's already an H. So if another H comes, it will become CH2. It will not show geometrical isomerism. For cis trans to be shown, remember, the two groups on each carbon have to be different. Therefore, for non-terminal alkynes, you will get a cis alkene if you do the hydrogenation using Lindlar's catalyst. So here we are. So I'm taking a non-terminal alkyne, reacting with hydrogen, Lindlar's catalyst, and you notice a cis alkene. Now another catalyst that can be used like the Lindlar's catalyst is called the brown P2 catalyst, which is nothing but nickel boride, Ni2B. Same logic is applied, hydrogen is adsorbed, and because of boron, it's not able to bind to all the active sites. Now the second one is called Birch reduction. Now here you are going to get a transalkene. So if you have an alkyne, a non-terminal alkyne, you can convert it into a cis alkene as well as a transalkene. Cis by using Lindlar's catalyst or brown P2 catalyst. And if you use the Birch reduction, that is this one, you will get a transalkene. So let's check out how that is happening. So in this reaction, an alkyne is reduced to an alkene by treating it with sodium or lithium and liquid ammonia. Any alkali metal will do. If the alkene can show stereochemistry, then the alkene formed is a transalkene. So you have the alkyne here, sodium in liquid ammonia, and you have a transalkyne. So let's check out the mechanism. Mechanism is pretty simple. Sodium, first of all, gets oxidized. Now, before I proceed further, let me make things a little bit easier for you. So, you know that if you want to check the hybridization of any carbon, this is the way you go about it. If you find 4 sigma bonds, you say it is sp3, right? If you find the carbon having 3 sigma and 1 pi, you call it sp2. If you find it having 2 sigma and 2 pi, you call it sp. Now, when the carbon contains charges, the easier way of doing, of course, not applicable every time, but easier way is, if the carbon has a positive charge, treat it like a pi bond. Remember, positive charge is not a pi bond, but treat it like a pi bond to find the hybridization. If the carbon has a negative charge, treat it like a sigma bond. And if it has a radical, treat it like a pi bond. What does this give us? If I were to ask you the hybridization of this one, so remember, plus is equivalent to a pi bond. So you see 3 sigma and 1 positive, which is pi bond. So 3 sigma and 1 pi is sp2. Suppose I have 3 sigma and 1 negative charge. Remember, negative charge is equivalent to sigma bond. So it is equivalent to 4 sigma bonds. So this is sp3. If it has a situation like this, remember, radical is also pi bond. So 3 sigma and 1 pi, it is sp2. So this way it will be easier for you to find the hybridization in intermediates. Now remember, at this stage you also need to understand that this is not a foolproof method, or this is not any method that can be used all the time. But most of the circumstances this will work. So let's check out further. All right, so here we go. We have the alkyne. We have the electron. Now this electron attacks one of the carbon atoms, and the pi bond shifts to the other carbon atom, giving rise to, what do you think it will give rise to? Don't you think you will get R, C, negative, double bond, C, radical, R? Because remember, this carbon is losing 1 electron of its own in this pi bond, but it is getting compensated by 1 electron from outside, so it will become a radical. This carbon is gaining the electron of this carbon, therefore it will become negative. What is the hybridization of this? How many sigma does it have? Can you see it has 1, 2, 3 sigma and 1 pi? What is 3 sigma and 1 pi? sp2. Now look at this carbon. It has got 2 sigma, 1 pi here, and this can be treated like a pi. So 2 sigma, 2 pi, sp. So remember, this carbon is sp, this carbon is sp2. So you get something like this. Remember, this carbon is sp2, it's planar, whereas this carbon is linear, if you notice, because it is sp, and it's got 1 odd electron, which is perpendicular to the plane of the carbon. So now what it does is, it takes 1 more electron. This electron again goes to the carbon with the radical nature. Now that also becomes C minus, and again this carbon will also become sp2. Which means this carbon will also have a R, it will also have a lone pair. But now it has an option of making sure whether the lone pair lies on the same side as this lone pair or opposite to this lone pair. What do you think will happen? Where would it like to orient its lone pair? Because it has got both the options. Because right now the odd electron is only in the p orbital. So don't you think that lone pair, if they are on the same side, they will repel each other more? So what happens is this brings the lone pair on the opposite side, which is why we get trans. Now remember these two carbons are negatively charged, two lone pairs. So both will take one H at a time from ammonia, giving an amide. Then the second one does the same, and you get a trans alkene. Now this reaction can also be used as a test. The solution of sodium in liquid ammonia is blue in color due to solvated electrons, which we know from our lesson in S block. Now, in the reaction, the blue color of the solution changes to colorless as the electrons are getting used up. Now, this reduction, of course, does not work for terminal alkynes. Now, this is weird because instead of reduction, you will have an acid-base reaction. See, what happens is, if you have this, and if you put sodium in liquid ammonia, the sodium is going to get oxidized. And since there is an H here, terminal H, and for alkyne, terminal H are little bit acidic, so the H plus will get reduced by taking the electron, and you will get a sodium salt of the alkyne, giving hydrogen gas. So you won't get an alkene here. The next one is something that we've already done in alkyl halides, dehydrogenation of alkyl halides, already discussed in alkyl halides. And I'm sure you remember that. Remember alcoholic KOH, we did E2. And then we did E1 for alcohols, remember? So all of them have already been discussed. And then comes something which we need to discuss, and that is dehalogenation of vicinal dihalides. Now, dehalogenation of vicinal dihalides is the elimination of two adjacent halogen atoms to produce an alkene. Now, dehalogenation of vicinal dihalides can be affected by either NaI in acetone or zinc in the presence of acetic acid or ethanol. That means if I have two halogens here, I can remove both the halogens, and that would either in the place of NaI in acetone or in zinc and methanol, and you'll get an alkene, you'll get NaCl, you get ICl, and you get zinc Cl2. Let me explain this. If you take zinc and methanol, this Cl and this Cl will go away. Okay, and the logic is pretty simple. Zinc gives two electrons. The two electrons will come, attack this Cl. This bond will go here and this bond will go here. So you basically get two chloride ions. Remember, this Cl will also become chloride because it is getting two electrons and losing only one. And this is gaining two electrons, so this also is chloride. So you'll get a zinc chloride. That is if you use zinc and methanol. If you use NaI in acetone, it is the I minus which is going to pull the Cl, and this Cl will go out. So Na will combine with this Cl to form NaCl, and this I would combine with this Cl to form ICl. So that is dehalogenation, again getting an alkene. Mechanism again is E2. So what I want you to do is, I want you to do this question. You have a meso compound, and in this meso compound, you need to do E2. You need to do dehalogenation and tell me which alkene you get. So pause the video, do it on your own. This is the solution. Now first what you do is convert this into a sawhorse projection. Remember, this will be the sawhorse of this. Now rotate the two groups in such way, since it is E2, both the Cls have to be opposite because it is dehalogenation, not dehydrohalogenation. So make them anti-coplanar. So this is your sawhorse. So this is your anti-coplanar. Now let's say I minus comes, attacks this Cl, this goes here, Cl minus leaves. You will get a transition state like this, and eventually you will get a alkene like this. And of course, obviously you get a trans alkene, that's because you used a meso. Now here I would like to specify two types of reactions, stereospecific and stereoselective. Now generally we do this in the case of alkyl halides, but I'm doing it now in the case of alkenes where it is more relevant. There are two reactions, stereospecific and stereoselective. Stereospecific reactions are those where there is one stereoisomer in the reactant, like just now we saw meso. And it only produces one stereoisomer as a product. And in this case, again, we saw it produced only trans alkene. It did not do a cis alkene. It only did trans alkene. So when one stereoisomer gives one particular stereoisomer, that is called as stereospecific reaction. A stereoselective is when a compound, which may be a stereoisomer, which may not be a stereoisomer, gives more than one stereoisomer as a product, but one of them is major. You have a reactant which may show stereoisomerism, may not, but on reaction, it produces more than one stereoisomer, maybe two, maybe three, but one of them is major. That is called stereoselective. It selects one of the stereoisomer to be major. Let's take an example. If you take an example of, let's say, a compound like this, now it doesn't really matter, even though this carbon is chiral, it doesn't really matter whether this carbon is R or S, it doesn't matter. What will happen is, if you get you get but1-ene, there is no stereochemistry there. You also get but2-ene. Now in but2-ene, you can get, remember it has got two hydrogens. So if it eliminates one H from here, you get cis, the other you will get trans. So when you get but2-ene, do you notice that this can give you both cis and trans? And both cis and trans are produced. So since both cis and trans are produced, but we know that they cannot be produced in equal amount because their stability is different. So ideally, hypothetically, they should form in equal amount, but since their stabilities are different, one will form more, trans will form more. That is stereoselective, where a reactant, irrespective of whether it can show stereochemistry or not, gives more than one stereochemical product, of which one of the product is major. One stereochemical product is major. That is called stereoselective. All right. So a stereospecific reaction is one in which one stereoisomer gives only one specific stereoisomer of the product. Just now we saw NAI in acetone gives us transalkene. This is stereospecific. Whereas a stereoselective is one in which the reactant gives product with more than one stereochemistry, but of them only one stereoisomer is major. Say for example, I take the same example of 2-bromobutane and treat it with alcoholic KOH, you will get, of course, I'm not looking at but1-ene, I'm only looking at but2-ene. You will get the trans and the cis but2-ene, and trans is major and cis is minor. And the last preparation reaction, as I said, it's a pretty short video. It's called the Kolbe's electrolysis. And in this, electrolysis of potassium or sodium salt of saturated vicinal dicarboxylic acid gives alkene. So you have this, and if I do electrolysis, obviously the CO2 will go, CO2 will go and both carbons will become radical and they become an alkene. For example, here, what do you think I'll get? Pause the video, make the product. Obviously, the two carbons will have a double bond, you will get propene. What do you think will happen here? Electrolysis. Again, remember, you will get but2-ene and you can get both cis and trans. And obviously, trans will be major. This is again a stereoselective reaction. And that finishes the first part, that is methods of preparation. So as I said, it's a short video. And these are the methods of preparation of alkenes. Most of them we have discussed in elimination reactions of alkyl halides. And so I hope you're able to understand this methods of preparation. Have a look at the video as many times as you want. Pause as many times as you want. Do all the questions on your own and only then check the answer by playing the video back. So with that, this is Kalyan Kumar signing off. Have a great and wonderful day and thank you for watching this.